Hi there! This video series is to display my problem-solving and learning abilities. I plan to show that I can solve any programming problem, regardless of whether I already have expertise in a particular language. I hope this helps others in my field to learn not just how to solve a particular problem, but how to teach themselves a solution to an unfamiliar problem. Currently, I am learning Python. I have no professional experience in the language and have only been learning it since mid-January. My only formal training is completing the Python for Programmers course on Execute Program. While I'm picking Python up fairly quickly, I cannot claim any real expertise. Today, I'm showing my approach to solving the 35th Project Euler problem from start to finish, vocalizing my thought process throughout. As always, I link to Project Euler and my repository in the description. Let's dive in. Problem 35, Circular Primes. The number 197 is called a circular prime because all rotations of the digits 197, 971, and 719 are themselves prime. There are 13 such primes below 100, and it lists them. How many circular primes are there below 1 million? Okay. So, first, we go ahead and we copy this question, and we make our little file. And then do our little copy paste that we do every time. Okay, so I'm gonna put a limit equal to 100 for right now. That low so that I know that we get the correct answer of 13. Okay. So, let's see. Search for okay, so we need these two methods again. As well as our primes array. And then effectively what we are going to do is for n in range let's actually move this down to here, so we have limit, and then we have a count equal to 1. And I'm starting it out at 1 because we know 2 is a circular prime. We could just as easily start out with 3 and have this be 2, 3. There's no excellent reason to have it one way or the other that I am aware of. So, but if we start here, we want to go to limit plus 1, or so below 100, below 1 million. Okay, so actually we don't need the plus 1 because we want that exclusivity. And then if is prime n, if it is prime, if length of n less than 2, then count plus equals 1. Goodness. Else if okay, so if the length is less than 2, then or let's just say if length equals 1, then we know that it is a circular prime. Else, and range n what we want to do is have a string n, which is equal to string of n, and then we want to do let's see. Okay, so our n dot append rn dot pop 0. So take the first element in this array, put it at the end of the array, and then we're going to put this array back into an integer. Obviously right now we're working with strings, but this will be pretty easy. All we have to do is like an rn dot join rn and this is going to be, or actually we can do this all in one step. It might be a little bit confusing, but we can. If not is prime, then is circular equals true. Is circular equals false. And break. If it is circular, then count plus equal to 1. Okay, so we might not even need this check. I don't think that check gains us anything, actually. And we might not even need this initial check. Let's see. Let's think about it with 3. We come in with 3. The length of n is 1. So it goes through the array 1 time. The appending and the popping effectively does nothing. It's still just the number 3 after we do the join and stuff. the number 3 is prime, so we want to go into the if. So is circular would be true, and we would add 1. So let's see if this works for what we have so far. Okay, so we're gonna just go ahead and make it a variable. It's not a big deal, but there. Okay, so we got 13, which is the correct answer for a limit of 100. So let's go ahead and it's 100,000. That's 1 million. See how quick this is. So this is probably going to take a little bit of time. Obviously taking much longer than the going up to 100. So let's see. So if you've been watching this series, you know about my isFactor method and my isPrime method. I've reused them several times. Basically, if the possible prime is less than 2, I return false. We don't actually need that in this case, but it's fine. Ooh. I have a feeling we might get the wrong answer. Well, no, because the 0 being there would make it... Actually... That should be outside of the for loop, so we're not recreating the for loop every time, because that would give us the wrong answer. So let's go ahead and cancel this. So we want to be sure we're rotating the number completely. Let's try that again. And we are making this a little bit... We are making this take a tiny bit longer. Another way we could do this is just calculate all the primes up to 1 million, and then analyze the primes to see whether they are circular primes. And if this doesn't complete within a minute, I'm going to go ahead and start working on that algorithmic approach instead, because the more I think about it, the more this is kind of gonna take us longer than we need it to take. Because there is a faster way of doing this if we just go through and calculate all the possible primes first. I have done it in some of my previous problems. Not that one, obviously. Let's see. Here's an isPrime. So this isPrime method, I just have for I in primes, if isFactor, then return false, because if it doesn't have a prime divisor, then it is prime. It's my logic. So let's make this instead. Yeah, it's already been way over a minute. Well, maybe not way over, but it's been over a minute and that isn't working. So let's go ahead and do the thing that we know is faster. And in this case, we don't even need to populate with that. We're gonna go ahead and this might make things take a little bit faster to set up, but it is going to make things a little bit faster overall, I think. So we don't even care about the return right now. Okay. And actually, I do want to copy some of that code. And then we want to do for p in primes is circular equals true. I actually do want a little bit more. I want this. Because that will save us checking again and again and again. The same numbers. Ooh. Actually, I will leave that just for future reference. I don't think it'll actually help us here. We're going to want to do this check. So, if is circular is true, we're going to have our string prime is the string of p. Our array version of the prime is equal to all the characters in the string, and then I'm not sure why I'm not copying and pasting. I wrote the code. Okay, so for n in range 2 to the limit, check whether it is prime, and then for every p in primes, we're going to check whether it is circular. So for I in range length of the string, we will modify the string once, where we will move the number, and then we'll bring back our count, and this time we'll start it at 0, which I feel is less confusing, obviously, because I did write a note when I was initializing it to 1. And then we don't need that extra space there. Let's back our limit down to 100 just to sanity check. Okay, so we got 13 there. And if anything, I think we got it a little bit faster, so that's a good sign for us. Okay, so we're back at 1,000,000. And this is going to take a tiny bit of... It's going to take a little bit. Okay. And if this doesn't resolve within a minute, then we'll have to think about other ways of optimization. Oh. Here's another way of optimization right now. So I'm going to do a print here. Length of primes Okay. Go ahead and cancel that. Okay, so obviously the longer width thing is just going. I'm going to go ahead and do another optimization here where I say if I is greater than the square root of the possible prime, break because there's no reason to continue testing primes that are larger than the square root. That should help us go through those million numbers a little bit faster. So, let's see. So, I feel like this is definitely one of those problems where it is easy to solve but difficult to optimize. Especially like we already had this as prime. I optimized it a little bit. I decided not to call as prime all over again for every member of the circle. But it's still taking quite a while to power through all of those numbers. Because as you can see, it hasn't printed out this, which means that we're still in this loop. And I'm not 100% certain how long this loop takes for up to 1 million. I feel like this actually might be hurting the optimization when we're going one by one like this. So I'm once again going to stop and restart, because as we get more and more primes, checking whether the item is in primes. Yep, that was our slowdown. That popped out immediately. So 78,498 primes under 1 million. So that's a lot. Checking whether something is in that array is a bit difficult. So now we know that that is our slowdown. We've optimized until then. Okay, so that did take under a minute. So technically within our time frame. Don't like that. Okay. So 55 is the number of circular primes under 1 million according to our algorithm. Let's see if Project Euler agrees. Yep, and only about 90,000 people have solved this before me, which is still a lot. So our algorithm was maybe not the most possible efficient algorithm, but it did give us this answer in less than a minute. We did discover that this was taking a long time because I was searching that array every time. Um, but doesn't seem like that big of a deal. Obviously, we would need to do some further optimization if we wanted to increase the limit and still run it under a minute. So I'm going to call that one done for today, and I will catch you in the next one.